Hello, everybody. Welcome to another lecture on set theory. The topic for today is going to be about the theory of function as it is developed in set theory. You remember that last time we introduced the power set axiom, and on that basis, we made a number of constructions, including perhaps the most important, which is the Cartesian product, which allows us to construct sets of ordered pairs where the first member is picked from one set and the second one is picked from another set. And then on that basis, we talked for a little bit about relations. So today it's the natural continuation of that topic where we move to the concept of function. So we're going to look at, well, what's a function per se, but also we're going to look at all the technical terms that are associated with elementary talks of function, as well as some of the basis theorems. Okay, so let me start going through the slideshow. Um, so I think that this concept of function that we're going to be tackling today is probably the most important of all the concepts that we've talked about so far. It has applications everywhere, not just in like pure mathematics and logic and things like that. Everything in the world that's somehow a process can be characterized by means of a function. So function are perhaps the most important tool to understand the world we live in. Now, of course, we're going to look uh, at things in a rather abstract way because we want to talk about functions in the most general way. Uh, but it shouldn't be forgotten that this is really one of the most important concepts. Now, we all have some level of understanding of what a function is. I doubt that any of you hear about the word function for the first time. We've all heard about that when we were in school. Um, and this understanding of what a function is that we have is for the most part intuitive, unless you've studied set theory before. And we think of functions more or less like a machine where you throw in something, some input, and then there's a sort of black box, and it gives you an output. So we think of functions mostly as those sort of machines that take an input and produce an output. Uh, and then you will be for sure familiar with that way of expressing function where we write f of x. Right, so let's talk a little bit more about that, because what we want to do really today is start from that intuitive understanding of what a function is and really take it to the next level. So here's an example of a function that you perhaps have seen before in school, or you might have seen something that is very similar to that. So let's start with the basic terminology that we are going to use in order to talk about a function. So typically a function is going to take an input. For that particular example, it's typically going to be presented as a function that takes as input a real number, unless you learn about that function at the university level, where perhaps you've seen it as taking as input complex numbers instead. But if you've learned about functions like that in school, it's typically going to be a real number. And that input is called the argument of the function. Now, of course, the word argument here is not the same as when we're talking about a premise conclusion argument in logic, but it's a perfectly well established sense of the word argument. Furthermore, the function is going to take an argument as its input, and then it's going to produce some output. In this case, it might be a real number as well. It might be the same real number that it took as input. Perhaps it's a function that happens to do nothing to that input. But definitely what it spits out is what is going to be called the value of the function at x, or for the argument x. So the value of a function is the output of the function. So that if we have an identity claim such as f of x equals y, then we say that y is the value of f at x. That's very standard terminology. I'm sure you've seen that before. Now, for each function that we are going to be considering, there's going to be two sets that are associated with it. A first set, which is the set of possible arguments of the function, and that set is called the domain of the function, and it's denoted dom and between parentheses f to say the domain of f. And the second set that's associated with the function is called the codomain, which is the set of possible values that the output will take. And it's denoted cod or code for codomain, code of f. All right? So whenever we're going to be talking about a function, we're going to know what its domain and codomain is. If it's not given, then it's not a properly defined function. So suppose we take an example where the domain of the function is A, the set A, and the codomain of the function is the set B. Then we're going to say that the function takes an object A as an argument, and it associates with it an object in B, the codomain. And often we're going to use the word maps in order to establish that connection. So we're going to say that the function maps an element of the domain on an element of the codomain, or maps onto an element of the codomain. In order to capture this idea that a function maps an element of the domain to an element of the codomain, we often use that notation that you see here, where we have f colon a arrow b. Now, sadly, the arrow is the exact same symbol that we use for the implication in logic. But as you see, it shouldn't lead to a confusion at all because it's prefixed by f colon, right? So it says f is a function of type a to b, where it maps elements of a to elements of b. Okay, so whenever we're going to be talking about functions, we're very often going to be describing them in this way. So there are different ways of describing functions. Often, in order to characterize a function, we're going to provide a formula that tells us how to go from the input and calculate the output. We take the argument, we apply the formula to it, and it's going to give us the value of the function. So from that point of view, a function is containing a sort of recipe to figure out what input is associated with what output. So then we say that the formula specifies a particular mapping of the elements of the domain to the element of the codomain. And that formula is going to be a general recipe, which is why we talk about a specific mapping, a general recipe to associate element of the domains with the elements of the codomain. So here's an example, and very often not in school mathematics, but in slightly more advanced mathematics, definitely in set theory, we will describe, instead of just writing f of x equals that formula, we can write f colon x, and then we have this interesting arrow here that has a little vertical line at the beginning. And it says f is a function that maps x onto that other number that we know how to calculate on the basis of having x. Now, of course, to know how to calculate that, we somehow need to know the property of multiplication, sum, subtraction, and real valued exponents, which we don't technically know yet. And by that, I mean, we haven't explained how to deal with numbers and those operations on numbers yet within the context of set theory, but we're going to get to that, well, next week. So for now, they're just used as examples based on your intuitive understanding of arithmetic, but we're going to revisit all of those things later on. Another way of representing a function is not by giving a formula, but rather by giving its graph, which should also be a familiar idea. I'm sure you've worked with those in school quite a bit. So for the function that we were considering, here's what its graph would look like on the interval going from minus 2.5 to 2.5. It's a beautiful shape, right? Perhaps that's a curve that's not flattened enough. Depends on the application. But definitely on that line, we think of that line as a collection of points where the first coordinate is the input, the value of the argument, and the second coordinate is the value of the output, the value of the function for that argument. So again, that should be fairly standard. Now, hopefully all of that is familiar. And just before we move on, you might be thinking, well, I already know what a function is. Why would we have to revisit that concept from the point of view of set theory? In particular, as we move along, you might feel that your intuitive understanding of functions is a lot safer or a lot more natural than what we're going to do here. What we're going to do might feel a little bit alien. And Tim Gowers, who won a Fields Medals in mathematics, the Fields Medal is like the Nobel Prize of mathematics, said the following funny thing about studying functions within the framework of set theory. He says, let me start with the most basic question of all. What is a function? This is one of the first examples of many, unfortunately, of a concept that you were probably reasonably happy with until your lecturer explained it to you. This is absolutely not a criticism of your lecturer. Thank you, Tim, who is excellent, by the way. Thanks again. It's more like a criticism of an entire mathematical tradition that goes back to the days when the foundations were laid for our subject in terms of set theory. So there are things that might feel a little bit unnatural about what we're going to do. And by feeling unnatural, I mean that feel less intuitive than the usual way in which you think about functions. But we're going to have to move on because, well, first of all, it's a course on set theory, so that's kind of what we're supposed to be learning. And secondly, as I'm going to try to explain, there are some important problems in mathematics for which it's absolutely essential to talk about functions in that particular way. So let's try to think about those cases. So what kind of problems in mathematics involve functions? Well, I'm going to mention three main kinds of problems. The first one is the easiest. We are asked to evaluate a function for an argument. What does that mean? It means that we are given a certain function and we are also given an argument, so an element of its domain. And by evaluating a function, we are asked to find what is the value of the function for that argument. So we are asked to find an element of the codomain such that the element of that codomain is the value of the function at x. So that's the easiest use of functions. We use functions like that all the time. But it's not the only way in which we use functions. We do use functions in many other cool, interesting ways that are definitely more intricate than this first one. So let's look at another one. Often in mathematics, those are called root-finding problems, and those are really just the inverse of the problem of evaluating a function that we just discussed. So here, instead of being given a function and an element of the domain, we're given a function and an element of the codomain. And we're asked to find an element of the domain such that the given element of the codomain is the value of that argument. Right? So here we're given f and y, and we're asked to find x. And a very well-known example that we've all learned about in school, I presume, is the famous quadratic equation, right? So we have a second degree polynomial and we are asked to find the value of x such that this polynomial equals 0. And that's about finding the zero of a function. That's a root finding problem. And of course, you all remember exactly the formula to find x. I'm sure you do. X equals minus b plus or minus square root of b squared minus 4ac divided by 2a. Yes, bravo, you remember. Give yourself a little pat on the back. You have not forgotten the essentials. All right, so that's a second kind of problem that we're often asked that involve functions. There's a third one, which is definitely more intricate than the first two. Because in the first two, we're given a function and we're asked to either find a value for an argument or find the argument for a value. Right? But the function is given to us. In the third kind of problem, the function is kind of the unknown. All right. So we're asked to find a function that has such and such a property. Typically, the property is going to be given in the form of an equation that the function has to satisfy. So what you're given is a property phi, and what you're asked to find is a function that has the property phi in question. Well-known example, if you've taken calculus, is you're going to be asked to find a function with real numbers as its domain and real numbers as its codomain, such that the derivative of the function equals the function. So that's a standard problem that you would have to solve in calculus. That involves solving a differential equation. So solving differential equations, they're all of this kind. For those of you who have done variational analysis, problems like that are happening very often as well. So as you reach a slightly higher level of mathematics, questions of the third type happen all the time. And in applications of mathematics, that's also extremely common. So now we're in the middle of this pandemic and people construct models. Well, all those models specify a property, which is a certain differential equation, and we try to solve the differential equation, which means we try to find a function that has the property described by the differential equation. So those things happen all the time. Now, that third type of problem will involve that sort of questions. How can I find a function with the property in question? Maybe I'll have a procedure or an algorithm that is going to allow me to find that function. If you take a course, say, on differential equations, you're going to be learning precisely the sort of algorithm that you need to do that. But sometimes you're given a property phi, and the question is not just, hey, can you find me a function that satisfies that property? The problem is there a function that satisfies that property? Like, for those of you who haven't learned too much calculus, you might be thinking, well, first, I don't know what's a derivative. Okay, suppose you know what's a derivative. The rate of change of the function f equals the function f itself. So that's cool, right? What would be a function that satisfies that? Is there even one? Maybe you don't know any function like that. But of course, the question is not, do you know any function that satisfies this equation? The question is there one? Is there such a mathematical object? Well, in this case, there is one. That's the exponential function, right? But there are many questions for which we want to know, does such a function that has this given property, does it actually exist? And if it exists, how many of them are there? Is there one? Is there a unique function that satisfies that property? Is there two? Is there infinitely many? How many of them are there? Those are very, very important questions. in applied mathematics and pure mathematics too, of course. Okay. Now, what I want you to keep from that discussion is the following. Let's focus on the second question. Is there a function that has the property in question? When you're asked a question like that, you're asked to quantify over the set of all functions, right? If 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 the collection of functions isn't really sharply defined, the answer to a question like does such a function exist, it's not well defined, right? Okay, if you find one and you succeeded, but if you didn't find one, you can't conclude either way. You can conclude that there isn't one because you don't have a reference class with respect to which you're making that claim. uh, so you might continue to search, but maybe it's in vain, right? So, so when we're asked questions of that type, our intuitive understanding of what a function isn't good enough. We need to go beyond that intuitive understanding. And this is precisely where set theory comes to the rescue. Uh, so often people teach set theory as emanating from logic, as a sort of continuation of first order logic. But really, when Cantor started to work on set theory, he was interested precisely in questions that had to do with mathematical analysis, where he was asked to solve questions like that. Okay, so this is, in my view, this is the true motivation for looking into that particular way of thinking about functions. Um, Again, it's not necessarily the most intuitive, but it has the merit of being crisp and sharp, and there's a certain beauty to it, which I hope you will appreciate. And for those of you in philosophy, you might just be wondering about what is the foundations for the claims that we make in mathematics. And so many of those claims are claims about functions, that having some sharp understanding of what a function is definitely beneficial. All right, so let's move on. Um, where do we begin? Well, so earlier on, well, last time, uh, we decided to deal with properties and relations, at least the extension of properties and relations, and we decided to treat them extensionally, so to treat them as sets. So for properties, we decided that they would be subsets of the domain of discourse. And for relations, there would be set of ordered pairs of elements of the domain of discourse. So we've talked about that. The Cartesian product allowed us to talk about that in a very rigorous and sharp way. And now we're going to try to do the same thing with functions. Now, functions, as we saw, they associate an argument with a value, an input with an output. That's really a relation, right? So functions are going to be treated as sets of ordered pairs as well. So whereas we normally use the notation y equals f of x, and we will keep doing so, we're going to understand that notation as meaning the pair whose first member is the argument x and second element is the value y is in f, right? So f is just a set of ordered pairs. That means that a function is just a special kind of relation. So every function is a relation, but not every relation is a function. They have to be special types of relations. So let's ask ourselves, what's so special about them? So let's have a look. So here's an example of a relation, and I've used the letter f not to suggest it's a function, but just to ask the question, is it a function, right? And we'd have A, which here will act as the domain, and B acts as the codomain. And here in my domain, I have 5 different elements, and I have 4 elements in the codomain. So I can represent my function as a set of ordered pairs like I have done here, but I can also do that graphically by putting arrows from the input to the output. This is why we're talking about a mapping of an input on an output. And now we want to ask, well, is this relation a function? It's definitely a relation because it's a set of ordered pairs, and that's all there is to it, right? But is it a function? Uh, so the answer is no, it's not a function, and there are two reasons for that. The first one is that f is not defined for the entire domain, right? So if we focus now on element A1, we see that A1 isn't mapped onto anything, right? So F isn't defined for A1. Another way of thinking about it is there is not a single ordered pair in F that starts with A1. That means F is undefined for A1. And that's something we want to avoid with functions. If you remember your intuitive understanding or your school education, that's definitely something we want to avoid. But similarly, but not similarly. In addition, there's a second problem, which is look at argument at element A4. That one is mapped onto two different things, namely B3 and then B4, right? So that means f of A4 is both B3 and B4. That's not something we want in a function. When that happens, we say a relation is one many because it maps one object onto many different objects. And definitely one of the things we want to avoid when we're dealing with functions are those relations that are one many. One input should go to one output, not to two or more outputs. Okay, so this is the basic idea, and that motivates our definition of a function. So let's go through it. Take two sets, A and B. Well, we're going to say a function with domain A and codomain B is just a relation, namely a subset of the Cartesian product of A and B. And we want this relation to satisfy two conditions. Those two conditions are the things that are so special about that kind of relations. The first is what we call totality. Each element of A is mapped on at least one element of B. That means that every element of the domain should be mapped onto something in the codomain. There shouldn't be elements for which it's undefined, like we had in our previous example. And symbolically, we would write for all x in the domain, there exists a y in the codomain such that y equals fx, or if you prefer, the pair xy is in the function, which is a little bit weird to say, but technically that's what we mean. And the second condition is uniqueness, which is the second flaw that we found in the relation we've examined. So take any element of the domain, and now take any two elements of the codomain. So if y is the value of x, and well, under f for the value of f at x, that's it. Yeah. So if y is the value of f at x and z is also the value of f at x, then it follows that y equals to z. That's a way of saying at least each element of A is mapped on at most one element of B. You'll remember when we were doing symbolizing in predicate logic, we talked about existence and uniqueness. We talked about things like there is a unique object with such and such a property. There was the existence and uniqueness parts. So here uniqueness is just the same idea that we exploited when we learned how to symbolize that sort of expression. So if we put totality and uniqueness together, what we get is that each element of the domain is mapped on at least and at most one element of the codomain. So that means each element of the domain is mapped onto exactly one element of the codomain. All right. So that's just what a function is. It's a relation that satisfies totality and uniqueness. Now, just in case you have forgotten, when we write something like that, that's called a restricted quantifier. If we write for all x in A, x has the property P. That means for all f, if x is in A, then x has property P. And similarly, if we say there exists an x in X such that Px, oh sorry, I should have written A. There exists an x in A such that Px means there exists an x such that x is in A and Px. So remember, this has the form of a universal positive sentence in the square of opposition, and this is a particular affirmative sentence. So this one has a conditional, this one has a conjunction. So I hope that's okay. We're going to use that thoroughly in our study of sets of functions, because otherwise the expressions like become so huge, they are unmanageable. And in fact, they're much easier to understand using restricted quantifiers. So we're going to be doing so all the time. So let's look at an example. So we're going to take a set A that contains 5 elements, 1, 2, 3, 4, 5. And then we're going to look at two relations on the set A, meaning that the domain is A and the codomain is A as well. So for the first relation, R1, we have four ordered pairs. So our question is this a function? And well, there's already a way of suspecting that it's not a function, because look, we have 5 elements in the domain, and we know that each element in the domain should be sent onto some element of the codomain. So that means we should have 5 pairs, right? We should have 5 pairs in the relation. We have only 4. That tells us there's one element of the domain for which the function is undefined, and that element is 5. Why? Because there's not a single pair whose first coordinate is 5. There's not a single pair whose argument is 5. And that means R1 is not defined for 5. So that's not a function. What about R2? R2 is not a function either. So let's look at what's happening. So what I suggest always that you do is go through the elements of the domain one by one for those simple examples. All right, so we see that there is a pair that starts with 1, so the relation is defined for this argument, and it maps it on 2. So far so good. Now what about the second element of the domain, 2? Oh, we see that there are 2 different pairs in that relation that have 2 as the argument, and one maps 2 to the object 3, and the other one maps it to 4, which means that there are 2 different objects of the codomain that 2 is mapped on. So R2 fails to satisfy uniqueness. Okay, so that example is meant to show A1 fails to satisfy totality and 2 fails to satisfy uniqueness. So this is a good way of thinking about it for the simple cases where the domain and the codomain are very small. So we can just list everything. Now that we have a definition of what a function is, we want to find when 2 functions are identical. So I'm going to introduce it as a separate definition here. We might look at those 2 functions and ask, are they the same function? Are they identical? Do we want to say f equals g? And if you check my algebra, probably you will find that they are not equal. I made a mistake on purpose. All right. Yes, so here we have 2 functions that are not identical. But what do we mean by saying that the 2 functions are not identical? Well, since functions are just set of ordered pairs, we could just use our general principle about identity of sets, which is the axiom of extensionality. So technically, we don't need a new definition for identity of functions, but we're gonna introduce one just just for convenience, which is going to happen to say exactly what extensionality would say. So two functions, sometimes we're going to list like f comma g to say f and g are both functions with domain A and codomain B. And we're going to say those two functions are identical if and only if they contain the same ordered pairs. That is to say, for all elements of the domain, f of x equals g of x. So this is using the notation that we've been developing. This is just what extensionality would recommend. Okay. So now we have a definition of identity of function, and we're going to use it many times in the theorems that we're going to be exploring in the later parts of this lecture and in the next ones. Now, earlier on, I mentioned that one of the reasons why we want to deal with functions from the point of view of set theory is that we want to form a set of all functions. Specifically, we're going to want to form a set of all functions with a given domain and a given codomain. So are we guaranteed with the axioms that we already have for set theory that there is such a set that contains all the functions with domain A and codomain B? And the answer is yes. Why? Well, because functions are just a particular kind of relation. And last time we've already seen that the power set of the Cartesian product A cross B does contain all the possible functions with domain A and codomain B. So that means we already have a set that is going to contain all the functions with domain A and codomain B. So now we're just going to take that set that contains all the functions and we're going to apply the axiom of separation to it so that we get a set that contains all the functions with domain A and codomain B, but nothing else, right? So as you see here, I take that set, power set A cross B, and I apply separation with the property f is a function. Again, go back to the definition. When we say f is a function, that means the first formula for totality is true and the second for uniqueness is true as well. That's what we mean. That's just a shorthand for that so that the definition doesn't look too scary. Now, the set of all functions with domain A and codomain B is denoted B superscript A, a bit like we denote exponentials in arithmetic. And the reason it's done is because the set of elements in the set of all functions is in fact growing exponentially, and we're going to study that again a little bit later. But that notation means the set of all functions from A to B. Okay? So let's look at an example of what that set could look like. So here I've taken A to be PQ and B to be TF. Why did I choose that? Well, I'm starting to make you feel like we're going to use function to study our logic a little bit deeper. So P and Q would be propositions or propositional variables, if you want, and TF would be true and false. So here what we're going to do is we're going to form the Cartesian product of A cross B. And since there are two elements in A, two elements in B, we know that there are four pairs in the Cartesian products. Those are all the pairs such that the first member is in A and the second member is in B. And now what we're going to do is we're going to form the power set of the Cartesian product, and then we're going to apply separation to find just the set that we need. And that's going to give us all the functions with domain A and codomain B. So let's form that power set. So since the Cartesian product has four members, how many members will the power set have? 2 to the power 4, which is 16. All right, so I've written it here. There is one element with 0 members, one element with 4 members. 4 elements with one member, one of the pairs, and 4 elements with 3 of the pairs, with 3 members, and then there is 6 elements with 2 of the pairs. If you know your binomial coefficients, that's how you find that, right? So you have to check carefully to make sure there's no repetition and that you didn't forget any of them. But I have 1 plus 4, 5, and then 5 plus 6, that's 11, plus 4, that's 15, plus 1, 16. So I know I have 16 elements, so I'm good. I've written my power set of the Cartesian product correctly. But now the idea is that each of those sets is a relation from A to B. So we have 16 different relations involving that set, those two sets. Not all of those relations are functions. So first, let's eliminate all of those that do not satisfy totality, the first condition for being a function. That means we're going to want to eliminate all of those sets that don't have a pair whose first member is each of the elements of the domain. So here our domain is P, contains P and contains Q. So we want to make sure we have at least one pair that starts with P and at least one pair that starts with Q. So the empty set is out. Those 4 sets here are out. So let's just restrict those a little bit. So we've managed to eliminate a few. Among the sets that contain 2 elements, look at the first one here. It has 2 pairs, but both begin with P. So it doesn't have one that starts with Q, out. Okay. This one here has 2 pairs that start with Q, not one that starts with P, out. It doesn't satisfy totality. Now, all of the ones with 3 or 4 elements will happen to satisfy totality. So what we're left with is 8 relations that satisfy totality. But not all of them are going to satisfy uniqueness, right? So we want to see if there are sets for which one of the member of the domain is associated with 2 different elements of the codomain. We see here that one here, right? P, T, P, F. What? It's associating P with both T and F, out. In fact, all of those with 3 or 4 elements are going to be out as well. So the elements that so out of the 16 elements, the ones that satisfy both totality and uniqueness are those 4 sets of ordered pairs. And the set B to the power A, namely the set of all functions from A to B, is precisely that set that contains 4 sets of ordered pairs, that is to say, 4 functions from A to B. So here we had 2 elements in the codomain, 2 elements in the domain. So let's just say take 2 to the power 2, it gives 4 elements. So if you had 3 elements in the domain, 2 in the codomain, you'd have 8 functions that you would have found here. So you can try it out, but it's really long and annoying. So I don't recommend it necessarily. All right, now that we have the basic understanding of what kind of relations functions happen to be, let's introduce a few concepts that we use to talk about functions, namely the range, the image, and then 2 other terms that will turn out to be identical from our point of view, pre-image and inverse image. Now I say that they're going to turn out to be identical from our point of view. I mean, for all those terms, you can pick 5 different books and there's going to be like 3 different conventions about how they use those terms. Those terms are used in pretty much all books that talk about functions, but many of those books use the words differently. So it's not like there's any sort of universal agreement about what those terms mean. Every book will have something that means what we'll mean by range, and will have a meaning, a word to say what we'll mean by image and pre-image and all of that, but there's variation. And if you allow me, I'll cite Tim Gowers, the Fields medalist again, who says, "It only remains for me to apologize on behalf of the mathematical community for the historical accidents that have led to this jumble of overlapping terminology and notation. You have no choice but to learn it and be very careful about using it. The only thing I would say is that one gets used to it, so much so that it becomes hard to remember what it was like to find it confusing." So in the notes, I give a link to the blog entry from which I took those two quotes. I strongly encourage you to go read it. It's actually very fun. But anyway, so I'm going to give one set of definitions for those terms, which is perhaps the most widespread, at least it's very widespread. And in any case, we have to pick one. All right, so we're going to take a function f from a to b. Right? Now, it might be the case that every element in the codomain B is mapped onto by some element of the domain, but maybe not. Right? If the answer is not, then we might want to think about the subset of the codomain that contains all the elements that are mapped onto by something. And that set we're going to call the range. So the range of F is going to be the set of elements in B, the elements of the codomain, such that there exists an X in A, the domain, and the pair xy is in the function, so y equals f of x. So that means that we want the elements in the codomain B such that they are mapped on by some element x in the domain. So that's what we call the range of the function. Now notice that B is the codomain of that function here. So really the range is defined by applying the axiom of separation to the codomain. And as a result, of course, the range is going to be a subset of the codomain. It's a trivial observation, but it doesn't hurt to just mention it. Now we want to distinguish the range from the image of a subset of the domain under F. So sometimes the range is called an image, and we're going to see why. But following our use, image is used in the following sense. So we talk of the image of a set under a function. So take a function with domain A and codomain B, and then furthermore take a subset of that domain. Okay? Now the image of that subset X under the function f, which we denote f of x, but now it's a capital X to make clear that x is not an element of the domain, but a subset of the domain. Okay? And now we're going to see f of x equals, by definition, the set of elements of the codomain that are mapped on, now not by an element of the domain, but by an element of the subset x of the domain. Right? So we take just a certain number of elements of the domain and we look at the set of objects that those map onto. And that's what we mean by the image of a set under a function. So here's an example. Right? So now we have a function with domain A and codomain B. Now look at, first let's check that it's a function, right? Every element of the domain is mapped onto at least one element of the codomain and at most one element of the domain. It's not like there's an object with two different arrows that go from it to two different objects. So that's a function. But now as we see in the codomain, there are three elements that are mapped on by something and two that aren't. Now, those two elements are part of the codomain, but they are not part of the range of the function, because the range of the function is those sets of objects that have an arrow pointing to it, that are mapped onto by something. So the range is the set B1, B2, and B3. Okay. Um, some people will call that the image of the function because it corresponds to f of a, namely the image of the set A under F. Now, A is a subset of itself, right? So we can apply our definition of the image of a set under a function. So if we take the image of the entire domain, then it gives you the range of the function. That's why there's a little bit of variability between how people define range and image. But hopefully our definitions are quite clear. Now here, just to understand what this concept of the image of a set is, let's look at now not the entire domain, but just the subset S that contains the first, the second, and the third element. And if we look, the first A1 maps onto B1, A2 maps to B2, A3 maps to B2 as well. All right. So the set of objects that elements of S map to is just the set that contains B1 and B2. All right. So the image of S under F is the set B1, B2. Hopefully that's okay. All right. So that's really all there is to it. It's really not a complicated concept, but it requires, it needs to be defined. Maybe just to understand how the concept works a little bit, we can prove a theorem to just start playing with our definitions a little bit. So the proof in prose is in the notes, and I'm just going to do a sort of Fitch diagram version of it. So the theorem says, take four sets A, B, X, and Y. And we're going to assume that A and B are both subsets of X, which is going to be the domain of the function, and Y the codomain. And we're going to want to say that the image of the set A union B under F is the union of the image of A under F and the image of B under F. So what are we going to do? So here I listed as premise what I'm given, just to keep the Fitch diagram a little bit smaller. Technically I should have made suppositions, but I wanted to not to have a diagram that's so huge. So I listed them as premise. The first line says f is a function with x as its domain and y as its codomain. That's what that first line means. The second line says a and b are both subsets of x, the domain of the function. And then, again, to show that two sets are equal, we're going to use our strategy based on the anti-symmetry of the subset relation. So we're going to show that the left-hand side is a subset of the right-hand side, and then secondly, that the right-hand side is a subset of the left-hand side. So here I'll just do the first direction, showing that the left-hand side is a subset of the right-hand side, because the other one works similarly. You really just change the order of the lines, writing the last first and vice versa, and it just gives you what you want. Okay, so now my conclusion is a subset claim, which means that for all x, if x is in this, then x is in this. So let me skip the step with the universal generalization and the definition of subset and just assume that some arbitrary element is in f of A union B. And I'm going to try to reach the conclusion that C is in the union of the images of A and B respectively. So you see, the same methodology that we've used, that we've worked on for months now to make proofs, is still coming handy here. Though the problems, well, okay, this one is not hard, but some of the ones we're going to look at are a little bit harder, but our methodology still applies quite well. So why don't we keep working backwards, right? So C is in a union, which means either it's in the first set or it's in the second set. That's just the membership condition for unions, right? Now we could try to use disjunction introduction or things like that, but I suggest that we just use the definition on each of the disjunct and give an equivalent disjunction. And it's going to be a little bit big and nasty, so be prepared. Oof. What is this? Oh, C is in the image of A under F. That means there's an element of A such that such that X maps on C, right? So there's an element of A such that f of X equals C. That's the membership condition for the image of A under F. Similarly, for the image of B under F, the membership condition is there exists an X in B such that C is the value of F at X. So now we have those two things here, right? Now I'm going to make a bigger step about logic here in order to fill in all the details, which I'm sure you can do. You'd use the definition of restricted quantifier in a few little facts, but here's what I want to say. There exists an X in the union of A and B such that X is the value of C, right? So that means there exists an X such that, applying the restricted quantifier, there exists an X such that either, parenthesis, either X is in A or X is in B, and, close parenthesis, and f of X equals C. And then we apply distributivity and we play a little bit and we reach that long line here. So I'm going to leave it to you to clarify how that step is made. But I hope you don't need too much time to understand that it is true, that it is correct, that's a valid inference. And the reason why I thought about starting from there to reach that sub goal is because, well, that line is just the membership condition for line 3, where C is in the image of A union B under F. And that means there's an element in the set A union B such that C is the value of F at X. Okay? So line 4 follows from line 3 just by the definition of image or the membership condition of images. Line 5 follows from 4, that's just logic. You have to play a little. Line 6 follows from 5, again, by the definition of image or membership condition of image, if you will. 7 follows from 6 just by membership condition for union, and 8 is the combination that I've used a number of times and that you folks have used as well, where we combine a conditional proof, universal introduction, and the definition of subset. You see, it's a fairly simple thing if you allow yourself to make all those steps. And that's why the proof in prose is, I think, like 3 or 4 lines, and I could have written it shorter, but I wanted to be fairly explicit. So that's our first proof, easy breezy. I hope it makes sense to you, right? So now we're gonna go on. Now that we've talked about our range, our image, we're gonna talk about another manipulation that we do with function, which is restraining them. So if we have a function f with domain A and codomain B, often we're not really interested in the entire domain A. We really want to focus on just one subset of the domain, all right? And then what we're going to do is we're going to define a new function on the basis of f. So from f, we define a new function where C is the domain of that new function. Okay, so start with a function from A to B and take a subset C of A. And now what we're going to do is we're going to define a new function, for now call it G, that has the same domain, that has C as its domain and the same codomain. And what we're going to want to make sure of is that this new function matches F for every single element of the domain. Okay, so for all x, the domain of G. So for all x in C, Gx and Fx are the same. Or if you want to think of it in terms of ordered pairs, that's how you would be writing it. Okay, so then we're going to say G is the restriction of F to X, and we have the following definition, F vertical bar C, to say F restrained to C. So that's the notation we're going to be using typically to talk about restrictions of a function. And if we have that relation between G and F, where G is the restriction of F to a subset of the domain. We can also say that F is an extension of G to A, right? So we have a function from C to A, from C to B. C is a subset of A. Now, of course, G is only defined for the elements of the domain C, not on everything in A, right? But we could grow it up to add a bunch of ordered pairs in it so that F is seen as an extension of G. Now, yeah, so I wanted to say that now, but I'll wait a little. So let's take a function from A to B. That's a little exercise that I have in the notes to make you play with that definition. And take C to be a subset of A. Okay. Now think of the image of C under F, and you're going to see that it's exactly the range of the restriction of F to C. So the image of C under F is the range of F restricted to C. Now you might think about it for a second and be like, duh, obvious. But I invite you to just try to prove it rigorously, because it's going to help you to understand precisely the definitions that have just been introduced. So often for those simple exercises, it's just about getting a better feel for the definitions. Now from that exercise, we see that we have the following fact. If G is the restriction of F to C, then the range of G is just the same thing as the range of the restriction of F to C, which is the same as the image of C under F. And now if we think of F as an extension of G to the entire domain A, and notice that there are many ways of doing that. As I said, you start from G, which is defined over the domain C, but C is a subset of A, right? So to extend G to be defined on the entire domain A, we need to add a bunch of ordered pairs whose first member is going to be all the elements of A that are not in C, right? And there are many ways of doing that. So that's what it means to say that there isn't a unique way in general of extending a function on a larger domain. Okay, so this idea of restriction of extension, it's not like the most useful thing in life, but in logic, in topology, in graph theory, it does play a certain role. So it's good to know about it. Now here's another thing that we do with function. Sometimes we start with an element of a set, we apply a function to it, and then we get something, and then we apply another function to that thing, and we keep applying functions sequentially like that, right? So we take an element x, it gives us a value f of x. Now maybe we take f of x as the input for a second function, right? And that will give us an output g of f of x, and that shows that from x we have applied now two functions, first f and then g. By the way, from that slide on, g is not, don't think of g as the restriction of f. G is just another function, right? So what we have here is that we apply functions one after the other. And the question that we want to ask is, can we think of applying a bunch of functions in a row as applying just one function that is perhaps a little bit more complicated, right? Or that is perhaps the net result of applying all those functions, right? Is this net result itself a function? And the answer is yes, right? So we're going to do it for two functions, but it applies more broadly. So the net result of applying G after applying F is itself a function, and it uniquely determines that function. Okay, so there are not two choices or more. And then we can prove that. And here's how we say it, right? So take two functions, one with domain F with domain A and codomain B, and G with codomain B, domain B and codomain C. So note that the domain of G is the codomain of F, because we're going to first apply F. It's going to take an element of A, send it to an element of B, and then G is going to take that element of B and send it to an element of C. And the idea is that if we apply G after applying F, that's going to determine a unique function from the domain A to the codomain C. Right? So it's like we shrank things. And that function is going to be such that the value of H at X is going to be equal to first applying F to X and then applying G to the result of that. Okay, so let's just look at how we would prove that. Oh, no, it's in the notes. I'm sorry, I'm not proving it here, I think. Or is it on the next slide? No, I'm not proving it here. It's in the notes. So here's an example of what's happening. Let's suppose we have a function that takes a natural number and sends it to a different natural number, to a natural number. It doesn't have to be different. But here it will be different because it maps x to x plus 3. And then a second function that also takes a natural number and sends it to a natural number. So we see that the codomain of F matches the domain of G. And G takes X and maps it onto 2X. So H, the result, is going to be the function that takes X and sends it to 2 times X plus 3. Because F takes X, sends it to X plus 3, and G takes whatever the result is and multiplies it by 2. So that's 2 parentheses X plus 3. So H would be that net result of applying F and then applying G to some object X. I hope that makes sense. That repeated process is so important that we're going to introduce a name for it, which is function composition, and we're going to have a little notation for it. So if we have two functions, one from A to B and one from B to C, and it's important that the codomain of F matches the domain of G, the net result is what we're going to call the composition of F and G, which is denoted G circle F, and it's a small circle. That means that you can read it as G after F. And that's supposed to be read as a single symbol, which is the name of that function, that net result. So on the last slide, I was talking about a function H, which is the net result. Well, so here we're giving a name to H, and that name is G circle F, or G after F. So there's going to be a function, right, such that for every element of the domain, the composition GF of applied to X equals first apply F and then apply G. Right? So that's just taking that new notation to define, to characterize the process of applying two functions in a row. And so that's the new notation. And then that just say, well, if you want to understand that one, it's equal to that other notation that we already understood from our agreements on how we use symbols before. So that's what function composition is. That notation is used very often, mostly in mathematics and computer science, a little bit in linguistics, a little bit in logic as well, but mostly algebraists in mathematics just love that notation. So there you go, you have it. One thing that we can talk about now that we have a symbol to talk about composition is to ask, what are the properties of composition? Is it associative, right? So here's how we can ask it. We have a function from A to B, then a second function from B to C, and finally a third function from C to D. And then what we have is, if we form the composite G after F, and we apply H after that, it's going to be the same as applying that function, h after g, to f. It just follows from that definition that we have here. So I'm not going to prove it, it's very easy. So function composition is associative. Now, is it commutative? Do you think g after f is the same as f after g? So in the notes, there's an exercise that asks you to show that this is not the case. As you might expect, it's fairly easy. Now, let's move on to the next thing. Now that we have our function composition, let's talk about one particular function that is quite important despite being very trivial. So when we were dealing with relations, we talked about the identity relations. The identity relation, which is the simplest, the smallest equivalence relation that one can have. And in the identity relation on S, so the domain and the codomain both are S, is just all the set of ordered pairs such that the first and the second member are the same. And moreover, for each element in S, there is such a pair so that it's reflexive as we would expect from identity. Now, turns out that, of course, this relation is a function too, if we ask ourselves. Yes, it is indeed. We can formulate that as a theorem as follows. So for any set X, any set whatsoever, there's going to be a unique function whose domain is S and codomain S also, such that f of x equals x. So f is the function that does nothing. It takes x as input, it returns x as output. Yeah, find your favorite example of a do-nothing person and say that's the equivalent for functions, all right? And of course, that function is identical to the relation 1s, which is why we use the same notation. And by that, we mean that that function here, defined as follows, contains exactly the same ordered pairs as the identity relation. So they are really the same thing. It's just two different names for the same thing. You might be wondering why we use that. Well, a little bit later on when we discuss inverses of functions, that's going to be a useful way to characterize some properties. But here's one example. That's like perhaps the simplest thing that we can do with identity functions. Suppose we have a function from A to B. Now, as we saw, for the set A, there's going to be an identity function on A, namely I sub A, that contains all the ordered pairs, one for each of the elements of A, and the first and the second element is the same. Similarly, for the codomain B, there's also going to be an identity function, one sub B. Right? So what happens if we compose F with the identity function? Well, you should expect that it does nothing, right? So F equals F after identity on A, which equals identity on B after F. Why is the order changing? Well, because applying the identity function on A first takes an element of A, gives you a new element of A. And then after that, you can apply the function f because it starts from A and ends with B. On the other hand, if you start by applying the function f, it's going to give you an element of B. So then you will apply the identity function on B. And as you would expect from the function that does nothing, the do nothing function, the identity function, composing a function with the identity function changes nothing. So that's what is expressed here. If you're having trouble understanding that, that might just be because it's too obvious and you're wondering why I would bother mentioning it. Okay, it's extremely trivial. Don't overthink it. One, the identity function changes nothing. It takes x as input and returns x, and then f will return f of x. So here, f takes x as input, returns f of x, and the identity function will keep it as f of x. So of course, f of x equals f of x. Easy. All right. Now we turn to a topic that is more delicate, right? So we've already seen a bunch of things. We can do with functions, we can restrict, we can compose, we can take image of subsets, and all of those things. Now we're going to be talking about the inverse of functions. That's a much trickier topic, but it's also a very, very, very important topic. So let's start from our talk of relations, because we did define the inverse of a relation last time. We denoted the inverse of a relation R superscript -1. It's very common in math to talk about inverse by superscripting. Did I say subscript? Anyway, superscripting -1. So R -1 is the inverse relation of R, and it's such that we just change the order of X and Y. Right? So if you start from X and you ask, hey, what element is R related to X? And you say, oh, it's Y. And then what element is R inverse related to Y? Oh, it's X. Right? So you came back with the same object that you started from. And that's really what should be happening with inverses, right? An inverse somehow undoes or does the opposite of what we started with. So when we come to functions, we saw, okay, functions are just a particular kind of relations. All relations have an inverse relations, but it might be the case that the inverse relations isn't a function. Okay, so when we're asking about the inverse of a function, where we're not asking about what the inverse relation is, we're asking really whether the inverse relation is a function too. So we have a function f, say, that satisfies totality and uniqueness. So that's the right kind of relation. That's why we call it a function, right? But then since f is a relation, of course, the inverse relation exists. But now we ask, is the inverse relation also satisfying totality and uniqueness? Is it also a function? So when we're saying, oh, here's a function, does the inverse exist? I really don't like that way of putting it. Really, it should be put in this way. Here's a function f. Is the inverse relation a function? I think that's a better way of putting it. However, I have never seen a math textbook that does it that way. So with this disclosure that I've just done, I will also talk about whether the inverse exists. Okay, so let's give the definition. A few times on last slide, I've talked about the inverse of a function. And I don't want to presume that there's only one such thing. So our definition is just going to say, here's the conditions under which some function counts as an inverse of the other one. And then we're going to ask, could there be more than one inverse? Right? So a function g from b to a is an inverse of a function f from a to b if and only if. First thing we notice is that the domain and the codomain are swapped. Why? Because to be an inverse function, g has to be an inverse relation. Okay, so g is an inverse of f if and only if for any element of a and any element of b, g of b equals a. If and only if, sorry, that's supposed to be the bidirectional arrow. If and only if f of a equals b, right? So f sends a to b. For g to be an inverse, it has to take b and bring it back to a. G undoes what f does. And then for the question of uniqueness that I raised is, well, is there just one way of undoing what f does? And the answer is, yeah, well, we're gonna see. I should have said spoiler alert. But yeah, spoiler alert, the answer is going to be yes. Okay, let's just start looking at some consequences of that definition of what an inverse of a function is, using some of the the tools that we've introduced already. So the first thing we find out is that if G is an inverse of F, then it follows that if we take an element of B, we apply G to it, and then we apply, that's going to give us an element of A, and then we apply F to it, that's going to return it to the element of B we started from. And the way we say that is that the composition F after G is the identity function of B. So the identity function on B is the do nothing function, and F after G is also is equal to the do nothing function. So that means F undoes what G does. And similarly, if we start with an element of A, we apply F to it, it gives us an element of B. Then we apply G to it, it gives us an element of A, and it returns to the same object. So applying G after F amounts to the do nothing function. So that means G undoes what F does. Okay, so that's the first thing to notice. Theorem, extremely simple. It's in the note, I believe. Play with it if you're not sure. It should follow very simply. Oh, I have it here. All right. So I thought I would give you a proof in Fitch style, though it's a bit loose. Right? We're getting a little bit looser as we go along. So the first thing I'm going to do is show that what F is a function, G is an inverse of F, and then I'll show the first identity, and the second is pretty much the same, so that's why I'll just show the first one. So our premises are F is a function from A to B, and then second is G is a function from B to A, and also it's an inverse of F. So that means that we're going to be able to use that part of the definition in our argument. And our last line is F after G equals the identity function on B. Now, I apply the definition of what it is for two functions to be identical with each other, a definition of identity of function. And that tells me, because here I have a function from B to B, here I have a function from B to A, and then one from A to B, so the composite is a function from B to B as well. So I say for every element of the domain, which is B, F after G applied to B equals the identity on B applied to small b. So here we have this equals this. So how are we going to show that? Well, remember that your restricted quantifiers are really conditionals. So we're going to suppose that an arbitrary element, oh, I'm so sorry, on line 11, instead of the small b, it should be x. What a moron, huh? It should be x. All right. So here what we're going to suppose is that for some arbitrary elements of the domain, it will follow on line 10 that our identity holds. And since it holds for this arbitrary elements, that means it's going to hold for everything. All right? Good. So now there are a few things that you want to notice when you're dealing with functions. Okay, so this is why I'm giving that example here. Now, suppose you have line 1, 2, 3, and then you have line 10, 11, 12. You might not be sure where to go from there. So here's one thing that you should notice. So now we have an element of B, and we also have a function whose domain is B, right? Now, since it's a function, G is total. It's defined for every element of the domain. So line 2 and 3 together give us an existentially quantified sentence, namely that B is mapped onto some element of A using function G. So there exists an X in A such that X equals G of B. That follows from the fact that G is a function, namely satisfies the totality condition, and from the fact that B is an element of the domain of T. Now that's an existentially quantified sentence. So then our earlier rule of thumb, which is always start with an existential elimination if you can, that kicks in immediately. All right, so this is why I gave you this little clarification about 2 and 3 implying an existential, and then our standard rules come back and we just apply the existential quantification directly. Okay, so then we're going to take an arbitrary letter and replace x by it. So remember, that means there exists an x such that x is in A and x equals g of b. So we have that conjunction as our supposition for the existential elimination. Easy, right? Our last line, we're just going to carry it within our subproof. And that's how it works with existential elimination. We've done a lot of them. And notice that line number 9 does not contain the letter A, right? It does not contain the letter A. If it did contain the letter A, that would be a problem because it would violate one of our conditions on the applications of existential elimination. But here we're going to be clean, right? So that's a sign that we're doing things in the right way. If our sub-goal contains A, that would be wrong, right? So what we're going to do is we're going to start from line 5 and try to manipulate it so that we reach line 9, and yeah, that's what we're trying to do. So first of all, on line 5, I'm going to look at the second conjunct, A equals G of B. But now, look at line 2. It says G is the inverse of F. So if A equals G of B, that means B equals F of A. And that's what I have on line number 6. It follows from 2 that G is the inverse of F, and from the second conjunct on line 5, B equals F of A. Now, when I define the identity function, it says for any object, applying the identity function to it returns the same thing. So the identity applied to B equals B. That's just the definition of the identity. So this is why there is no line number. And then on line 8, I'm going to apply the definition of composition plus what I have accumulated on my line so far in the subproof. So I'm going to start from F compose G applied to B. Why? Because that's my sub-goal. That's the left-hand side of that equation. Now, the definition of composition tells me this is equal to F of this particular object called G of B. But now I said G of B equals A. So that thing here is equal to F of A. But now on line 6, I said F of A equals B. So that's what we've got here. But also we said B equals the identity applied to B. So we have that identity here. So since we have a series of identity, that means the first term equals the last one. And then we get line number 9. And we're happy. Right? So typically when people prove theorems about functions, they wouldn't use Fitch diagrams or things like that, but I promise you that it's still going to help you to be much more efficient at writing proofs involving functions. And if you're in math or comp sci or engineering or physics or linguistics, or if you do more logic in philosophy, or even if you do modeling in economics or whatnot, you're going to have to understand a lot of things about functions. And that's where that methodology that we've developed for doing proofs is going to follow you, right? It's going to assist and guide your reasoning. So I hope you like that thing. Even if it's a very simple proof, it shows how it's beautifully cast as a Fitch diagram. So now we get to that second consequence of our definitions. I mentioned that if F has an inverse, then it has exactly one inverse. Okay, so I'm not going to do the proof here. But remember what it means to prove that something is unique, that there's a unique thing satisfying a property, where here the property is being an inverse function of f. Right? So you suppose that both g and g prime are functions that are inverses of f. What does that mean? We apply the definition that we have here for what it means to be an inverse of the function f. And on the assumption that both g and g prime are inverses of f, you're going to show that they have to be identical. And for that, you're going to use the definition of function identity. And you're going to see it's a very simple, very short proof. But again, I encourage you to do it just as a sort of way of playing with your definitions to become more comfortable with them. And because of that theorem, now we're justified in speaking in the way I instinctively did when I turned to the topic of inverses, which is to say the inverse of a function f as opposed to just an inverse of a function f. Normally, when we use the definite article the, that means there is a unique thing, which is an inverse of the function f. Linguists might say, oh, but there's all those counterexamples. Yeah, that's true. So let's say a proper use of the definite article the means that there's a unique element, which is an inverse of the function f. So now we're justified in talking about the inverse of f. And since there's just one of them, we might as well use a particular notation for it. So if g is the unique inverse of f, then instead of writing g, we're just going to use that standard notation f superscript minus 1, which means the inverse of f. Now I just want to draw your attention that I don't confuse the notation f inverse of x with f of x exponent minus 1. If you remember your algebra, f of x exponent minus 1 just means 1 divided by f of x, which isn't the same as the inverse of f, except in very special cases, but definitely not in general. Okay, so this possible ambiguity is a little bit unfortunate. But I'm trying to teach you standard notation here, so that means dealing with suboptimal notation that is very widespread. All right, so there is a unique inverse to a function. Now, the next thing that we're going to talk about, and that's the last one for this lecture, is the inverse of that thing that we discussed before, namely taking the image of a set under a function. And so you have the image of a set under a function. And now we're going to take the inverse image. And another name that is used for it is the pre-image. And most of the time, those two terms, pre-image and an inverse image, are used in a synonymous manner. Okay. I'm going to use pre-image because, as I'm going to explain, there's something rather perverse about the notation, and I think the term inverse image kind of reinforces that perversion, so to speak. So I'm going to use the term pre-image, and I would advise that you do so as well. All right, so we start from a function from A to B. And now we're not going to take a subset of the domain, we're going to take a subset of the codomain, okay? And then the pre-image of x under f is just the set of elements in the domain that's mapped onto some elements of x, right? So the x's in A, the domain, such that the value of f at x is in the set x. And then the pre-image of x under f is denoted f superscript minus 1 of x, the set x. And people will often read it as f inverse of x. Now, that's the first level of perversion. Okay. Before mentioning that, I just want to give you a particular case. Sometimes X, the subset of the codomain, is going to be a singleton because we're trying to figure out all the objects of the domain that map onto that element of the domain, say B. Okay. Then F inverse, the inverse image of singleton B under F is called the fiber of F over B. I'm mentioning it because some of you might take a course in topology, though it's not taught very much at SFU. And if you do, you're going to hear about fibers all the time. So a fiber is a particular case of a preimage. Now, the reason why I say this notation for the inverse image or the preimage is terrible is that if you look at the definition of that set, it doesn't presuppose that F has an inverse, right? Some functions have an inverse, some functions don't have an inverse. The preimage is perfectly well defined, even if F doesn't have an inverse, okay? Which is why I prefer the pre-image rather than the inverse image. And I would also like it if we dropped that notation, but that's the notation that's used everywhere, okay? So just keep in mind the pre-image is defined even if the function has no inverse. And again, I'm apologizing for that notational depravity that I have I'm not responsible for any of that. So let's just look at what it could imply. So here are two little theorems. I believe I prove one in the notes, maybe here. Yes, I do prove one here. I think the first one. And the second is left as an exercise. Now, we start from a function f from a to b, and then we take a subset of the domain, right? So first, we're going to take that subset of the domain, and we're going to find the image of S. And then remember, pre-images take a set of elements of the codomain. Now, the image of S is a subset of the codomain, right? So we're going to take S, then take its image, and then take the pre-image of the image of S. And what we're going to find is that there could be, as a result of doing that, more elements in the set that results than we started from when we have S. So S is going to be a subset of the preimage of the image of S. But in general, it's not going to be an identity. We're going to see later. So a little bit of a thriller. We're going to ask later, when is it that S equals the inverse or the pre-image of the image of S? Anyway, we're going to prove that on the next slide. And then the other theorem says, well, take an element of the codomain. First, take the pre-image of T, and then take the image of the pre-image of T, and that could contain fewer elements than T. So that is going to be a subset of T. Try to do that proof based on what we're going to see for the first one, just to play with the definitions a little bit. So here's what it would look like in a Fitch diagram. And I've put it all at once now. So our premises are f is a function from a to b. Then we're going to take a subset S of A, the domain, and we want to reach the conclusion that S is a subset of the preimage of the image of S. That's a mouthful. After teaching that a few times, just say that like it's normal English and all of that is cool and perfectly reasonable, that it's, a sensible way of talking. But what we're introducing here is not a sensible way of talking in everyday life. It's about how to function properly in the world of mathematics. And in the world of mathematics, that's considered perfectly normal to talk like that. So, 7, our conclusion is about showing that something is a subset of another one. So we're going to suppose that some arbitrary element, I choose C, is in S, and we're going to try to show that it's in this other monstrosity. Now, the first thing I'm asking myself when I have a subgoal like that is, let me try to write the membership condition for the inverse image, right? So I go back to my definition here, and I have the definition of the pre-image of the set X under F. And I'm like, okay, but now I'm not taking the pre-image of X, I'm taking the pre-image of F of S. So I'm just going to rewrite that, replacing X, capital X, with F of X, F of S, right? So that's what I did on line 5, right? So the pre-image of F of S is that set here, where I've just replaced the X here and here by F of S. So now I know what it means for C to be in the pre-image of the image of S. It tells me that I need an element of A, right? Now C is in S, and S is a subset of A, so that means C is in A. Trivially satisfied. But I also need to know that F of X, here C, right? F of C is in the image of S under F. Okay? Now, if C is in S, that means, again, go back to the definition of the image, that means that F of C is in F of S, right? So the value of F at C is an element of the codomain, which is in the image of S under F. So from 3, 4 follows directly. But now 4 is my membership condition on line 5, right? So now I have C, an element of A, and F, right? And I know that F of C is in F of S. That's my membership condition. Both parts are satisfied, and that means C is in the inverse image of the image of S. Almost too easy, isn't it? So that's what we have here. So we've introduced functions. I've talked about why we want to deal with functions as a part of set theory. There are parts of math for which it's very important not to just use our intuitive understanding of functions. Then we've introduced a few different kinds of manipulations that we can do with functions, namely restrictions, compositions, composition with identity functions, things like that. We can take the inverse sometimes, not always. We said if a function has an inverse, it's unique. Nothing tells us yet when exactly do functions have an inverse or not. But that's exactly what we're going to look at in the next lecture video. We're going to refine our understanding of inverses to provide a sort of general condition for when do functions have inverses. Okay, so stay safe, stay healthy, sleep tight, and I'll see you in the next video. Bye.